Welcome to Guided Practice for Lesson 14.1, and this is all about rational numbers and types of numbers and classifying numbers. So, first off, write all the names that apply to each number in 7/8. And you might be thinking, well, it's a fraction. But we need to be more precise about that because now we have some new vocabulary, and this is a chart here that's good to know about. So, real numbers. Okay, real numbers are made up of rational numbers and irrational numbers. Now, a rational number is a fraction. It's a fraction of integers. Let's go back to what an integer is. An integer is a positive or negative whole number. So, like -3 is an integer, and I can put in even 2 is an integer. -8/2 is because that could be -4. Also, 0 is an integer, but I'm going to erase that because now I can even go into, well, integers are made up of the negative. Let me do this. So they're made up of the negative whole numbers and the positive whole numbers, like the square root of 9. That's 3. 5 is a positive whole number. 8/2 is 4. 0, that works as well. These are all whole numbers. And so the whole numbers make up also the integers. So the integers include the negative whole numbers and the positive whole numbers, including 0. And then the rational numbers, well, like I said before, it's a ratio of integers. 7 is an integer, and so is 8. 1 is an integer, and so is 3. And when you divide these, they become specific kinds of decimals. Like 1/3 is 0.333, and that keeps on going. So it can be a repeating decimal, and like this is 0.2121, and so on. That can be repeating decimals are okay, and terminating decimals like that 0.97, that's okay because 0.97 is 97/100. So that it can be made into a fraction of integers. Even this one, the square root of 16/9, that is 4 because the square root of 16 is 4 and the square root of 9 is 3. That could be a fraction of integers. See, all those are good. But the irrational numbers, yeah, those cannot be turned into integers. Like this one, this goes on forever, but there's no pattern to it. It has to be a repeated pattern. This is a pattern. It has 3 0 and then 3 and then 2 zeros and then 3 zeros and so on, but it has to be a repeated pattern like the 2 1 2 1 2 1 2 1. That's okay. This is a decimal that goes on forever, which is okay, but it has no patterns to it. And all these like this, the square root of 2 over the square root of 5. Don't know what that is. Square root of 8. What times itself is 8? You might be thinking 4, but that's wrong because 4 times 2 is 8, but we need 4 times 4. That's 16. So I don't know what it is times itself is 8. And in fact, what I will do is this. As far as square roots go, I'll go with, we can have the square root of 1, and then I'll do the square root of 2, square root of 3, square root of 4, square root of 5, square root of 6. I forgot something here. I made a mistake on that. I meant to make this a specific color. Square root of 4, square root of 6, square root of 7, square root of 8. The square root of 9, I'll make a different color. See, these are all rational, but the white ones are irrational. So the square roots in between the perfect squares, right? And by the way, let me tell you real quick, why are these numbers called perfect squares? Well, 1 is a perfect square because you can make a square out of it. 1. 4 is a perfect square because you can make a square out of the number 4. And then, let me make those bigger. And then 9 is a perfect square because you can go 1, 2, 3, 4, 5, 6, 7, 8, 9. It's a perfect square, right? But the numbers in between those perfect squares are irrational. So only the starred ones are rational. So and that list just keeps on going. So anyway, you got a lot of information here. Let's get into this. Write all the names that apply. Well, it's just a fraction of integers, and so that is rational, and if it's rational, then it's also a real number, right? Everything that we're dealing with here is all over here, real numbers. Okay, number 2, the square root of 36. Well, I know that the square root of 36 is equal to 6, because 6 times 6 is 36. And so this would be, 6 is an integer. And in fact, it's a whole number. So it's a whole number. And if it's a whole number, then it's everything else. See, this is a pretty good chart here, because if it's a whole number, then it also is inside of the integers, which is inside of the rational numbers, which is inside of the real numbers. So if it's a whole number, it's everything. That's why I got that going there. Okay, next, square root of 24. I have no idea what the square root is. It's pretty darn close to square root of 25, but that means it's going to be one of our irrational numbers, which also it's a real number. And yes, there is such a thing as non-real numbers or imaginary numbers, but that's a high school topic. 0.75, that can be expressed as 0.7. Oh God, of course it can. Hello. It could be 75 hundredths, 75 over 100, and that's a fraction of integers, so that is a rational number, which is also real. Oops. Okay, next we'll go with 0. Well, where is 0 in this whole thing? We can see here that 0 is right here. So it's a whole number, and it's an integer, and it's a rational number, and it's a real number. Oh, you can't see that, huh? It's a real number. So whole, oops. Sorry. Whole number, integer, rational, real. So that's why we got this going on right here. Now, the square root of 100 is, square root of 100 is 10. And then that negative goes right there. So negative 10, we found out what negative 10 is in this whole thing. And negative 10 is an integer here. It's a negative whole number. So if it's an integer, then it's a rational number and a real number. So that is what we have. And then we have 5.45. Now, this, I'm going to tell you now, this is equal to 5 and 45 over 99. See, one other thing that I'd like to show you is if we have, I like using white here against the black. So if we have 0.1, that is in the tenths place, so we call that 1/10. But if we have 0.1 with a bar over it, that's 1/9. And you might be wondering why. Well, if we do cowboys and horses on this, we have 9 going into 1. 9 doesn't go into 1, but it does go into 10. And 9 goes into 10 one time. And then I'm just going to keep dividing this. And you might see a pattern here where it just keeps on going, 0.1, which brings us back to, well, that whole thing is that. So for now, I'm going to tell you why is this equal to this? Because when you divide this, you end up with this decimal. Okay? So I'll keep going here. 0.2, that's 2/10, but 0.2 with a bar over it is 2/9. 0.3 is 3/10, and 0.3 with a bar over it is 3/9 or 1/3. 0.4, yep, that's 4/10. 0.4 with a bar is 4/9. 0.5, hopefully you get the idea here. 0.5 with a bar is 5/9. 0.6 with a bar is 6/9 or 2/3. 0.7 with a bar is 7/9. 0.8 with a bar is 8/9. And oh boy, 0.9 with a bar. So think about that. 0.9, and the 9's going on forever. is the same thing as 9/9 or 1. Isn't that weird? It's totally weird. But we're going to be using this idea here to answer this. So if you have 0.45 with a bar over it, that's 45 over 99. See, however many numbers are under the bar is how many nines you're going to have in the denominator. All right. So we're going to use this here. That's why I have 45 here. It's 45 over 99. And now we have, well, this right here, this counts as just a rational number because it's really just a fraction here. So that's why we have this, rational and real. And number 8. Okay, this counts as 18 divided by 6 is 3, not 6, 3. And you have a negative there, so negative 3. What kind of number is negative 3? Well, it is an integer. And as I've shown you before, an integer here is a rational and a real number. So it's just these 3, not a whole number. And that's why we have this. Okay, so number 9. Tell whether the given statement is true or false and explain your choice. All whole numbers are rational numbers. Let's look here. The whole numbers here are inside of the rational numbers. So yes, that is true. All whole numbers are rational numbers. Yeah, it's so, and it's when inside of it. When it's inside of it, it's called a subset of the rational numbers. It can be written as a ratio of the whole number to 1. Okay, so no irrational numbers are whole numbers. No irrational numbers are whole numbers. That's a weird way to say that. There are no irrational numbers that are whole numbers. Oh my goodness. There are no irrational numbers that are whole numbers. Yeah, I'm thinking. Oopsie. What just happened? Sorry about that. The whole numbers are rational numbers. Yeah, the whole numbers are definitely rational numbers. So we have this here, no irrational numbers are whole numbers. Yeah, the whole numbers are definitely within the rational numbers and not the irrational numbers. We got that line going right there. And identify the set of numbers that best describes each situation. Explain your choice. So the change in value of an account when given to the nearest dollar. Well, when you're talking about the nearest dollar, those are whole numbers, right? Because if you have, let's say you have $10 and you spend something that is $3.10, your change is what? It's 90 cents, $6.90, but you're identify it. So the change in the value of an account when to the nearest dollar, well, to the nearest dollar would be 7, which is a whole number. So it'd be integers. The change can be a whole dollar amount, and can be, oh yeah, it can be positive or negative because you can. It could be 0, yes, but it could be negative because you could spend more than you have, and then you end up owing the money. So there you go. The markings on a standard ruler. Well, it could be, you can have 4.5 feet or 0.75 feet or something. So that sounds like a rational number to me. Rational numbers. The rule is marked every 1/16 of an inch. That is true. Oh, we have this here, right? So yeah, every 16th of an inch right there. Okay, and finally, what are some ways to describe the relationship between sets of numbers? And what we have is this. You can describe one set as being a subset of another or show the relationship in a Venn diagram, which is like the Venn diagram would be like this here. This is our Venn diagram right here. All right, so there's the guided practice for classifying numbers, lesson 14.1. Thanks for watching.